Okay, so let's talk about 6.6 nuclear energy. And the first thing we need to talk about now, we don't need to know as much chemistry as you would have learned in, say, your chem classes for nuclear energy, but you do need to understand the difference between fission and fusion. And so that's those terms, really, not so much the process. And then you also need to understand what a half-life is and how to calculate a half-life. And so basically some calculations surrounding half-life. So we'll talk about that. So here's what you need to know about nuclear fission. Nuclear fission is really the only type of nuclear reactors that we have at this point to generate electricity because fusion has not really been harnessed effectively yet. They're racing to figure out how to use nuclear fusion. So fission is where you break bleh, break a atom apart. Basically, you break the nucleus apart, and fusion is where you join them. And nuclear fusion would create tons more energy from those radioactive elements than fission would. But fission is kind of all we've got right now. Okay. But basically, with nuclear fission, a neutron is fired into the nucleus of this unstable radioactive element. And the element that we use most commonly in nuclear power plants at this point is uranium 235. It releases a ton of energy. And so when that energy is released, it's released as heat. And then more neutrons then break apart. It just creates this really extreme chain reaction that happens super quickly. And so we can harness all of that energy to heat water, just like we did in all the fossil fuel notes. We talked about heating that water to create steam. Steam turns the turbine, that whole process. So that's something that you need to know. Um, and so the radioactivity refers to the energy that's given off by the nucleus of the isotope. And so radioactive, the nucleus actually decays or breaks down, and then that energy is released even without fission. This is just a natural process that happens. But we've discovered that we can actually collect that energy all at once by causing this to happen much more quickly than it would naturally. So that was a really important discovery. Excuse me, when nuclear fission was discovered. All right. And so what do you need to know? Oops, I don't know why that popped up, but what do you need to know about half-lives? Well, first of all, a radioactive half-life is the amount of time that it takes for 50% of a radioactive element or radioactive substance to decay or break down. Excuse me, let me get a drink really quickly. So you probably remember this from chemistry, but an example that we have over here is cobalt 60. So if we start off with 10 grams of the substance, one half-life would be how long does it take for that 10 grams to decay and turn into just 5 grams of cobalt 60? And so the time that it takes would be considered one half-life. And scientists have discovered, and cobalt 60 decays rather quickly. It takes about 5.27 years for 50% of the isotope to decay and turn into something else. I'm not even sure what cobalt 60 turns into. I don't have that memorized. Um, but what does, that's basically what what a half-life is. So I think you probably remember that from chemistry. So some more common elements that we think about are uranium 235, which is what we're talking about when we're talking about energy production. Its half-life is 700 million years, which will be important later. And then carbon 14 is something else that we use commonly. We use it in geology, biology a lot when we're um, kind of aging substances. And so we can do something called carbon dating. And the half-life of that substance, carbon 14, is 5,730 years. And so half-life can be used to determine a variety of things, including the rate of decay. So how long is it taking that element to decay? And then also what's the radioactive level of a substance at any given point? And so again, just being able to calculate a half-life is something that's important. And we'll talk about that more when we talk about calculations. Generating electricity. So, how do we use nuclear fusion, or sorry, not fusion, fission at this point to produce electricity? Well, it's exactly like we talked about with coal. So, we heat up water. Um, and we heat up the water with rods of uranium 235. So we see this is a nuclear reactor core, and in this is the whole entire reactor here. Okay. And in the core is these rods, and the rods are made out of uranium 235. I would not want to be the person that makes those uranium rods. That seems really dangerous to me. But it's basically we keep these in a lead core because lead actually stops the radioactive material from flowing through. That energy it stays within it, kind of insulates that energy within the within the core itself. Um, and so it heats up the water. So we pump water into the core over top of these rods, and it heats that water with all that energy that's being released is heated up to a really high point where it makes steam. The steam, I'm going to repeat this over and over. The steam turns the turbine. That's what a turbine looks like. It's basically a fan. The steam runs over it, it turns that fan. And then the turbine's connected to that generator, which is that electromagnet that spins and creates electrons, which flow. The electron flow then is collected at a transformer, which turns that into a usable energy, which is then transmitted to our electric grid. All right. And then the other side of this, so that's the generation of electricity, just like we've talked about with everything else. And then we also, just like we have with the coal-fired power plant, we also have this really hot water then that we need to cool in a cooling tower. And it's non-radioactive water vapor because all of the radioactive material is stored within the reactor. So when we've had meltdowns, the meltdowns have occurred within this reactor, not with any of the rest of the power plant, but within the reactor itself. And so usually it's the lead. The building's usually made out of lead because it does kind of insulate or stops the radioactive materials from getting out. But that lead cracks or something, it overheats to the point. Usually it's this core that overheats and cracks. The lead cracks, and then all that radiation is able to escape through the cracks. And so that's what a meltdown is. But so we have the same issues here with this hot water cooling. And the issue isn't necessarily with all this steam that's coming off, it's with the warmed water that we put back into rivers and things that are close to nuclear power plants. Okay, so essentially, like we talked about these control rods, they get lowered into that reactor core. Um, and then we have this water pump that brings in cold water to cool down. These are like things that happen so that we don't have meltdowns or explosions. The cool rods are placed into this reactor, slows down the reaction. We have a water pump that brings in cool water to again slow down the reaction so it's not overheating too much or too quickly. And then we have this cooling tower that allows the water to cool down before it moves back into the core. So all of these things are kind of in place to sort of prevent any issues with the process. There's lots of fail safes along the way with a nuclear reactor to keep it from being a problem and from melting down. All right. And so I do tend to think of nuclear energy as being renewable because it's so plentiful. We have a lot of, and because we get from such a small amount of fuel, we get a ton of electricity, but it's not actually renewable. It's non-renewable. Um, because the elements that we get the radiation from, like uranium, are limited on the planet. The best thing about nuclear energy is that it's a lot cleaner than fossil fuels. When a meltdown happens, it's a serious problem, but very few meltdowns have occurred over time, and it is so much cleaner than fossil fuel. There's essentially no air pollutants, so there's no particulate matter, there's no SOxes, there's no NOxes, there's no CO2, there's no methane being released when that electricity is generated. The only thing that releases the greenhouse gases is mining the uranium and building the power plants themselves. So in the short term, there are releases of greenhouse gases, but then in the long term, we can use that uranium for quite a while, and we can use the power plant for years, and so there's no greenhouse gases over time that are being released other than mining the uranium. The only gas that's released from the electric generation is the water vapor, like we talked about. Water vapor technically is still a greenhouse gas because the water mixes with the carbon gas to form CO2, but it stays in the atmosphere, but very briefly. The hydrologic cycle is constantly happening. So it does put water vapor back into the atmosphere, but if there was less carbon, there'd be less carbon for that water to react with, which would actually be a good thing. So the real main drawback of nuclear energy are the potential possibilities for meltdown, but that's why there's so many regulations and safety precautions that go into place and lots of fail-safe steps along the way to stop a nuclear meltdown. And then the radioactive contamination with the uranium rods, as well as the waste, like when we've spent the rods and there's no fuel left to create or generate lots of heat, what do we do with the rods? And so those spent fuel rods need to be stored somewhere, and they're usually stored on site in lead containers at nuclear power plants. But they also go to what we call Superfund sites, which I actually got the opportunity to tour when I was a professor in South Carolina. I got to tour the Savannah River Power Superfund site where they store nuclear rods in these lead containers, and they put the lead containers in glass containers. And so, in case it's like a double layer of protection. And then they put these large, I mean, it's probably 30 feet tall rods and containers. And then they put those 30 feet rods underneath the ground in non porous surfaces or in non porous rocks. And they store those underground in areas that don't have a lot of seismic activity. As you can imagine, you wouldn't want to store these in California, but they did store them in South Carolina, about 30 minutes south of my house. So that was kind of cool that I got to go see that. And so here are the big tanks. You can see when I say about 30 feet tall, that's the size of the tank. That's how long those rods are. And then they can actually store those underground as well. Okay, and then the mine tailings, so the tailings left over at the mine where they're, mining their uranium out of the um, rock themselves. So any of those tailings need to be stored somewhere. And so it's like with any other mine, they store it in, hazardous material landfills and things. And then there is water that's used in the process of the, electricity generation. So that can actually create some thermal pollution. And decrease when you increase the heat. I think I've mentioned this before in class. When you increase the temperature of water, less oxygen is stored. So that's why global warming is such a problem. As we increase the temperature, less oxygen can be stored in water. Same thing happens with thermal pollution. We increase this temperature of the water in the nearby riverways and stream waterways, and then that decreases the amount of oxygen, and it creates dead zones essentially in the river. So that's a real problem. You can see here like a satellite imagery of a power plant. Okay. So this is like a reservoir where they dump a lot of really hot water, and then they dump the cool water into the waterway, and you can kind of see with this infrared image, how much it's actually heating up compared to the rest of the water. And with all pollution, you're going to hear me say that the solution to pollution is dilution. And so as you dump pollution, the thermal pollution, it's going to mix with the other water around it and cool, and so eventually it will all turn back to, that dark blue color like it should be. But that thermal pollution can be a real problem in the area of the reactor, the power plant. Okay, so some famous nuclear meltdowns that you need to know about. There's actually three. And the three are um, 3 Mile Island in the United States, Fukushima, Japan had a nuclear meltdown, and also Chernobyl, which is in Ukraine, had a meltdown. So 3 Mile Island in the US was a partial meltdown due to a testing error. They were testing out um, the nuclear power, and there was a problem, and a lot of radiation was released, and it really caused the disaster of 3 Mile Island. But there were no deaths, and there were no residual cancer cases because of that incident. And then Fukushima, Japan had an earthquake and a tsunami that triggered one of the cooling pumps to fail, and so, because the core then got too hot, it led to a meltdown, which was an explosion basically of the reactor core where those control rods are stored. And there was widespread radiation release in Japan. And so, that was a real problem. And then also Chernobyl in Ukraine, it had a stuck cooling valve that wouldn't open. And so, and the valve is what controls the water, the amount of water that's moving in to the core. And so that valve wouldn't open during a test, and it ended up leading to a complete meltdown. It was a disaster in Ukraine. The reactor core exploded. There were several deaths of employees that worked at the plant, and we've had generational issues with the area because of the widespread radiation release that occurred in Chernobyl. And there are still, to this day, there are still genetic issues with people that were impacted, excuse me, from that reactor meltdown. So this is, excuse me, this is a reactor under normal conditions. We have lots of cool water in there, keeping the uranium or the radioactivity temperature of those rods lower. This is what happens. The water level decreases and those rods get way too hot, and then it cracks the lead core, the lead walls of the reactor. And so the environmental consequences of meltdowns include genetic mutations, cancer in the surrounding area to both people, animals, and plants due to that released radiation. Contaminated soil, and then that radiation can spread through the wind over long distances, affecting ecosystems, far away from the meltdown site. So Chernobyl has been studied, why has they've studied it intensively because it happened so close to the local area. And you can actually measure radiation as far as Spain and Scotland, Ireland, Finland, Sweden, all the way south here, into Italy, and these countries here. And so this radiation just traveled long distances because of that wind. And so here's your practice FRQ for 6.6. Identify and describe one letter in the diagram above that is common to both nuclear and fossil fuel electricity productions, and describe when it says describe. So identify is name it, describe is actually, um, write information about it, and then describe and identify one letter in the diagram that's only found in nuclear power plants, and describe what it does. And that's it. If you have any questions, make sure you talk to me in class, and I'll see you all soon.